In this video, we're going to investigate a special group of series called alternating series. And also we'll learn different tests that we use to check different kind of results concerning alternating series. Well, alternating series is a series involving terms with alternating signs. In all these series, the A1, A2, A3, A4 are supposed to be all positive. So with this kind of structure, we can see the sign alternates from positive, negative, positive, negative. In an alternating series, the first term can be positive, can be negative. There's really not much difference because we can always, for example, in this series, pour out the negative one. So all we need to do is just worry about this type of alternating series. Now, this kind of series are special because, well, you have a lot of positive terms, a lot of negative terms. It's natural to guess the conditions required for series to converge will be probably weaker because we can see internally some values get canceled out because of a lot of positive terms and other negative terms. This is just our guess. Well, let's see exactly the condition under which this kind of series will converge, and you'll see indeed the conditions are weaker than those conditions we normally require for series to converge. The test we have for alternating series is called alternating series test, or AST. Alternating series converges if 1. The limit of the general term approaches 0. If this is true, you can put the power of -1 here is still true, and this condition is minimum because we know for any series, whether it's alternating series or any other series, if such condition is not satisfied, series will diverge. That was our nth term limit test for divergence we learned before. So anyway, this condition is necessary. So it's nothing actual at all. Now there's another condition that says a sub n is greater than or equal to a sub n plus 1. Now this basically says a sub n as a sequence decreases as n increases. So a sub n is a decreasing sequence. Well, these are the two conditions we need to check to determine whether a series converges. Like I said, this condition is necessary. This condition is sufficient, meaning if that's satisfied, series converges. Now, if it's not satisfied, we just don't know whether series will converge or not. Well, let me quickly explain why these conditions are weaker than normal. For example, if just those two conditions satisfy for a normal infinite series may not converge. Famous example is our harmonic series. Check out this series. Say n start from 1. Limit of 1 over n is 0. Condition 1 satisfied. 1 over n as a sub n decreases as n increases. Obviously, we can tell, right? So both conditions seem to be satisfied. Yeah, we know this series diverges. So for normal series, those conditions alone are not good enough. But for alternating series, it's enough. So for alternating series, under seemingly weaker conditions, series would converge. Alternate series would converge. It's exactly because of a lot of negative terms, a lot of positive terms, they just cancel out, making it possible for the sum to be a finite number. That's the basic idea involved. But the rigorous proof require advanced knowledge in mathematics, but we don't want to get into. So what we'll see just is how to apply this alternate series test to check convergence, divergence of alternate series. Alright, let's see this series. It's an alternate series. Anytime you have power of -1, whether it's n plus 1 here or n, that's going to make the sign alternate. It's an alternate series. Difference is if you have n or n plus 1, your first term may be positive or maybe negative. It doesn't matter. They're all considered as alternate series. And we all use the same test, alternate series test, AST, to check that. So two conditions. Alright, let's first identify our A sub n. A sub n is the part you see without the power -1. So we can check two conditions. One, is the limit 0 when n goes to infinity? It is. When n goes to infinity, this is infinity, 1 over infinity is 0. So our first condition is satisfied. Then we move on. If first condition is not satisfied, you stop. You just say series diverges, because if the limit is not 0, any series will diverge. Now, condition 2. A sub n as a sequence. We want to check whether sequence decreases as n increases. Usually, we don't compare two consecutive terms because it's difficult. Well, in this case, it's clear. A sub n compared to n plus 1. This is greater because the denominator is smaller. See, got n here and this is n plus 1. So it is obvious. It's true. And this is true for all n. So condition 2 is satisfied too. Therefore, we claim by the alternate series test, the alternate series given in this problem converges. Check two conditions. See another example. Again, we first clearly identify the A sub n. This is A sub n. We check this condition and this condition without the power of -1 involved. Okay, first condition, limit n goes to infinity, n over 3n squared plus 2. Well, the limit is obviously 0 because the bottom is square approaching infinity, top is first part of n approaching infinity, bottom is a higher order, or you can apply low beta rule. Check that. Now we check condition 2. Condition 1 is okay. Condition 2, we're going to show somehow, or we're going to check whether this sequence decreases. This time, it's not easy to compare A sub n to A sub n plus 1. Let me write it down, you can see why it's not clear. Well, compare A sub n and A sub n plus 1. In A sub n plus 1, the numerator is bigger. Normally it would make the fraction bigger, but then the denominator is bigger than the denominator there too. Normally that would make the whole fraction smaller. So it's unclear. When we increase both the top and the bottom, it is overall the fraction greater than that or less than that. It's not clear, so we cannot compare easily. Algebraically, sometimes it's still possible. We're not going to do that. Instead, we're going to try to check decreasing or increasing of this sequence using what we learned in calculus. Treat this as a function of n. The idea is, if the derivative of this is negative, it decreases. Alright, so let's pretend n to be x, continuous variable. Let's just differentiate. So let's differentiate the n, a sub n with respect to n. Now that's quotient rule. So we're going to have a 3n squared plus 2. N is like the variable, continuous variable. So we can actually differentiate. Square quotient rule. So forget about this guy. We are applying quotient rule. So we differentiate the top as 1, 3n squared plus 2 minus n times derivative of the bottom, 6n. Simplify this. This is 2. This is 6n squared. This is 3n squared. So combined, it's a negative 3n squared over 3n squared plus 2 at the bottom. The bottom is square. We never have to worry about that. Now, a sub n as a function of n has derivative which is negative. You can see if n is large, this is a constant, n approaches infinity, so at least you can tell this will be less than 0 for large n. How large? We don't care, because n approaches infinity anyway. N approaches infinity, so as a matter of fact, for n equal to 1, this is already negative. And sometimes, even if this is not negative for the first finite number of n's, like if you have like a 12 here. So for n equal to 1, equal to 2, this may not be negative. That's not going to bother us. All we care about is whether this is a negative for large n. As we always said, convergence or divergence of an infinite series depend only on those terms when n is very large. Anyway, this case, a sub n prime, derivative of a sub n is always negative. From what we learned in calculus 1, this is decreasing as a function of n, which means a sub n is more than a sub n plus 1. Now we verify that condition 2 is satisfied too. So we draw the conclusion because of the alternating series test. The original series here converges. So you see how we apply the alternating series test to check convergence, divergence of alternating series. Condition 1, check a limit. Condition 2, normally you treat it as a function and see its derivative is negative or not. If it is negative, it means it decreases. So condition 2 is satisfied, then series converges. Now if somehow your derivative is not negative, you cannot tell. It just means you cannot verify this condition, or it's inconclusive. You cannot say one way or the other. Just test fail. So overall, this alternate series test, condition 1 is necessary, must be satisfied for series to converge. In other words, if it's not true, it diverges. If it is true, we move on. And the second condition, if it is true, series converges. If it's not true, we don't know. Now, for alternate series, we're interested in other results too. There is something called absolute convergence. It says, given alternate series with alternating signs, everything. Now we say, if sigma an without all those negative signs, no, we turn everything positive. We like take absolute value of everything to get the sigma an only. So this result says, if, or definition, if sigma an converges, then we said the original alternate series converges absolutely. Now it's exactly because the way we would get sigma n, we would take absolute of everything. Every turn we take absolute value, number we drop negative signs. This would become sigma n. That's how we come up with this name. This result says more about the alternate series. It says, in the original series, there are positive terms and negative terms. Now, if this is true, we're saying even if we turn all those negative guys to positive, series still converges. That's what it means. And mathematically, we can prove if the series converges absolutely, the original series will converge. That's just another result we know. It's true, we're not going to prove it. All we need to know is that it's a better result. Alright, there's something else called conditional convergence. Well, let's see what it says. It says, if we take absolute value, get that, right? Get the series here, and this series diverges. Yeah, we can show at the same time the alternate series itself converges. Then we say the alternate series converges conditionally. Well, terminology is a little misleading. Somehow it seems that alternate series converges conditionally somehow is weaker than converges. That's not quite true. It just says basically the alternate series in this case just converges. We cannot expect better result. Well, we cannot expect the series to converge absolutely. That's really what it means. So when we say conditional converges, we just basically get the convergence of the series itself. Series converges. But if you take an absolute value, it's going to diverge. So the negative guys matter in the sum. That's really what it is. Alright, so now giving alternate series, we could expect a different kind of outcome. Maybe the series will converge absolutely. That's like the best result. You take absolute value, series still converges. That's great. Or you take your absolute value, series diverges, but series itself actually converges. In this case, we say series converges conditionally. There's another outcome that is the alternate series itself just diverges. Maybe because the limit is not 0. So with all these different outcomes, how do we sort it out? What should we check first? Now I have this chart to follow to check a different kind of outcome. First, we check sigma an. It's like we take the absolute value of everything already. Check this series for convergence. So this is the action in red. Well, we check this for convergence using appropriate test. Any test that works, basically. Well, there are two possible outcomes. We check this for convergence. Maybe the answer is yes. If the answer is yes, we draw a conclusion. Sigma -1 to n to the power an, the alternate series itself converges absolutely. That's because of this. If sigma an converges, then we said alternate series converges absolutely. Now, if the answer is no, we check this for convergence. So no, it won't converge. Then we check the series itself, alternate series. The alternate series itself for convergence. And this time, we can only use alternate series test. For alternate series itself, there's only this alternate series test we can use. Again, we use the alternate series test. The series could converge, the series could diverge. So if the answer is yes, we claim that the alternate series converges conditionally. That's because of the definition here. See, the sigma an diverges because it doesn't converge. So that's this part. And say the answer, of course, we assume the answer to be yes. And sigma, the alternate series itself, converges. According to this, we said the alternate series converges conditionally. Now, if the answer is no when we check the alternate series itself for convergence, then we simply say series, the alternate series diverges. So this is like the best result, and this is, well, just the series itself converges. Alternate series self converges, cannot expect better result. Well, this just says alternate series diverges. It's mostly because this condition is not satisfied. Because the condition 2, if it's not satisfied, we don't know. We cannot say for sure the series will diverge. But anyway, this diagram gives us the idea, how to approach alternative series to check different kind of outcome. Let's see one example. Then I'm going to check for absolute convergence, conditional convergence, or diverges for this alternative series. Let's follow the chart. So the red boxes indicate the actions. Those circles indicate respective outcome. First, check C1AA for convergence. So check sigma AN, that is without the power of -1. Check this for convergence. Here. Well, how do we do it? I'm going to try integral test because I can see such integration is not bad. Say we go from 2 to infinity. Remember integral test, we can choose any lower limit we want. Well, this with a simple substitution like u equal log x will become u du basically, or log u. That's like a log x. Plug in infinity, plug in 2, or plug in infinity, again infinity. So this thing diverges. That's infinity. Improper integral diverges. Then the infinity series diverges. So the answer is no. This one diverges. The answer is no. And we're going to go this way. 2. Now check the original alternate series itself. This part we can only use the alternate series test. So first condition, a sub n is log n over n. The limit actually is 0 because, well, when n goes to infinity, this is log infinity, that's obviously infinity. We can apply Gauss rule, or we can compare order. Log is a lower order compared to power. This is the first power. So have a higher order on the bottom, lower order on the top. The limit is 0. So condition 1 is satisfied. Condition 2, you're going to see whether it's possible to show this thing decreases. Well, it's not obvious if we compare a sub n to the next term. Next term we would turn n to n plus 1, increasing the top. The bottom n to n plus 1, increasing the bottom. So when bottom and top are both increased, it's hard to compare. So we're going to just do it like how we usually do. Treat this as a function. Find its derivative. See if we can show the derivative is negative. If the derivative is negative, this thing as a function decreases. So of course, as a sequence, it would decrease too. So let's again use the quotient rule. So it's n squared on the bottom, derivative of the top times the bottom minus log n times 1. Quotient rule. So this is 1 minus log n over n squared. Now, well, we know all we care about is when n is large. We can tell here when n is large, the derivative is indeed negative. Starting from actually 3, log 2. If you plug in n, you plug in 2 for 2, log 2 is less than 1. So plugging 1 for n, 2 for n, the value of the derivative is actually positive, but we don't care about that. We only care about n large. For example, n greater than 3. Once n is greater than 3, then the whole thing becomes negative for any n greater than or equal to 3. Anyway, so we've shown it decreases for large n greater than or equal to 3, including 3. Now, alternate series test says the alternate series converges. Converges, yes. So we went through this. Answer is no. When we check this, answer is yes. Then we say this series converges conditionally. Let's check this series. Again, we take a sub n, we identify a sub n. So first, sigma a sub n is sigma 1 over n to the root of 2. So we're going to check this series for convergence. Well, actually, we can tell here this approaches 1. The limit of a sub n is 1. According to our test for divergence, we can tell this thing diverges. Now, how do we know the limit is 1? The bottom, let's check the bottom. N through is a 2 to 1 over n. Now when n goes to infinity, this goes to 0, so this is going to approach 1. Therefore, 1 over that will approach 1. Alright, so we check this sigma n for convergence. The answer is no. And then we check, okay, we're checking this. Now we check the alternate series itself. It's 2. Now this time I'm going to try alternate series test. Always this part. We're here. Well, check 2 conditions. 1, the a sub n. Well, like we already find out, this thing does not approach 0. It approaches 1. So the first condition in the alternate series test, first condition is not satisfied, and then we know right away diverges. According to our chart, for doing this, the answer is no, it doesn't converge. So we conclude that the alternate series diverges. That's our final answer. Let's see one more problem involving the flow chart being using. So first, again, we're going to take absolute value of everything. So our a sub n will be n over 2 to the n. So first, we check sigma an, which is sigma n over 2 to the n. Alright, what test are we going to use? Well, we'll try a comparison test. So let's see. Well, first we need to estimate. Actually, I'm trying term-wise comparison. So I believe this series will converge. Well, this is a. Let me copy it down first. How do I know this series will properly converge? Because the bottom is exponential, the top is power. So I know when it goes to infinity, this thing goes to infinity fast, very fast. And in this problem, notice there's no term I can drop. Yeah, I can still kind of come up with some estimate which turn out to be correct. But most of the time, when you apply term-wise comparison test, you try to drop terms so you have a clear p-series or geometric series. Well, there's nothing we can drop. Yeah, I still believe this would converge. So what I'm going to do is to try to make this bigger. Let's see. I'm going to first do this. I'm going to split the bottom as n over 2 times 2 n over 2. Alright, well, this is like a square root 2 to the nth power times square root 2 to the nth power, basically. It's a little tricky, but it's going to work out. So, well, when n goes to infinity, this is exponential base greater than 1, so this goes to infinity fast, much faster than n. In other words, this thing is greater than that. So I can claim this is true. When n is large, I don't care about n small. When n is large, this is true. It's like, for example, it's like, say, now if you split algebraically as square root n times n over this part, I'm dropping the part that's less than 1. That's less than 1, so the product is less than that times 1. That's how I got this inequality algebraically. And this is clearly going to give me a convergent geometric series, because like the R there, this is my Bn basically. That's it. That's a convergent geometric series. R equal to, that's less than 1. So I've shown a sub n is less than b sub n, which is geometric series. This sigma Bn converges clearly as a geometric series, so I know sigma An converges. Alright, so I'm able to somehow come up with the required inequality. Okay, so I'm checking sigma n for converges. Answer is yes, and then this thing converges absolutely. That's my final answer. I threw this example, and it shows you, sometimes even though there's no term you can drop, I can still apply the term-wise comparison. Now, well, from the last two examples, you can see when I was trying to check sigma an, where an is all positive, because I took absolute value of everything to get that. When I was checking this for convergence, in one example I used integral test. Another example I used comparison test. So this part could be whatever test we learned so far, whatever it works, and that's a positive series. Now we're going to learn new tests that can be used to check this part too. Here are our two new tests. One is called the ratio test, other is called the root test. In each test, we actually take the absolute value of everything involved, like here and here. So the series we check are not limited to just nicely alternating kind of series. Could be just sigma any infinite series. Could have positive, negative, in whatever order. So with those tests, we can always conclude that no matter what kind of pattern, if any, positive, negative, that kind of pattern, some positive is and then a group of negative, or anything at all, we can tell if the limit we call the rho here as less than 1, the series will converge absolutely. In other words, we take absolute value of everything, it still converges. If rho is greater than 1, the series diverges. Same here, root test. We take absolute value anyway, so if the limit, this limit n goes to infinity. If the limit is less than 1, the original series with positive, negative, any order, any fashion would converge absolutely. If the limit is more than 1, series diverges. Each test, if rho is 1, the test fails. We don't know. We would have used other tests, whatever other tests that may work. Alright, so those are the new tests we're learning here. Now, well, what's the difference between those two tests? Clearly, we're doing differently to find the limit of rho. In this case, we're comparing two consecutive terms, the ratio. It's a sub n plus 1 versus a sub n, which is the term immediately before that. This test, we take nth root. We take nth root of absolute value of the general term. Let's try the limit. Now, before I show you an example, let me quickly explain to you why these results are true. Well, take this as an example. Say, in this case, rho is less than 1. So the limit of this ratio is less than 1. let's see, suppose this is 1, this is our limit row, the limit is less than 1. So well, because the limit of this fraction is row, eventually all those fractions are going to be close to this guy, the value of row. Then we can find the number. You can imagine you can find a number, say called k, between 1 and the row, such that all the fractions will be less than k, because well, they're going to be all very close to the row, because the limit is row. So for large n, all right. So I'm trying to kind of prove this result here. So we can tell all those fractions will be less than k. Okay, an less than k. That's always true. In other words, a sub n is less than k a sub n. Well, let's just, for simplicity, let's start from a2 less than k a1, a3 less than k a2, which is less than, because a2 is less than that, so it's like a k squared a1. From this we can conclude that a sub 4, if we keep doing this, we'd have a k to the third power a1. a5 will be k to the fourth power a1. Now if we add all those a1, a2, a3, a4 up, it's like adding those guys up. That's like converging the geometric series, because k, you can see, is less than 1. That's the idea. Okay. So similarly here too, we be able to come up with sort of a converging geometric series to compare more than one diverging geometric series. But anyway, if it's little hard to understand this part, that's fine. This is proof that that is not our focus. Just trying to kind of explain to you. If you understand, great. If not, no big deal. Anyway, so we're going to mainly focus on how to apply this test to check our series for convergence divergence. Before we hit the examples, let me point out that this series is necessary if this result this test is necessary if a series contains a factorial. We talk about the factorial. N factorial is n minus 1, n minus 2 times 3, 2, 1. So we always check, see if there's factorial. If there's factorial, we must use this test. If there's no factorial, and say there's nth power, we'll probably try this test. Alright? That's okay, let's see this example. Now there's a power of -1. We're going to take an absolute value anyway, so any result we find out will give us, actually either it's absolute convergence or divergence, because we always take an absolute value, or those tests will fail if rho is 1. In that case, we would have to try something else. But anyway, so let's use appropriate test to check this one out. Well, here we see n factorial and n power. Because it's n factorial, we must use the ratio test. So let's set up the limit. See what it is. See if it's less than 1 or more than 1 or equal to 1, in which case we will have to try different test. Okay, now I'm going to write down the a sub n first on the bottom, so based on that I can more easily come up with a sub n plus 1. So here just copy down the term including the power of -1. That's a sub n. Top, I'm going to replace n by n plus 1, so everywhere, so it's n plus 2 now. There's n plus 1 factorial. Oh, I'm running out of space. So let me squeeze the n plus 1, n plus 1. So I got a sub n plus 1 on the top, a sub n on the bottom, and take an absolute value. Well, first of all, we take an absolute value. This is gone because whether it's positive or negative, it's gone. Take an absolute value, make it everything positive, so that's gone. So now I'm left with that divided by this. So I simplify. Copy down the top. Now I have plenty of room. That's this part. And flip this. All right. Let's see what's going on here. Well, the reason we must use ratio test whenever there's a factorial is we can simplify the factorial a lot. Let's see. Example, I got n plus 1 factorial divided by n factorial. Let me do it on the side. You can see this guy, if you write it out, that's like n plus 1 times n minus 1 and so on. And this part, the tail, is n factorial, so those two just cancel out. Those two parts just cancel out. We're left with just n plus 1 on the top. So that's gone. This will cancel out. There's just n plus 1 left on the top. Well, there's n plus 1, there's n plus 1, so I have actually, let me just copy down. So I only have an n plus 1 to the n power. Well, what's the limit? N goes to infinity. What's the limit? It's not very clear. Let me write it as n over n plus 1 and then let's see, there's actually a shortcut, but yeah, how about it? Let's take a shortcut. I'll explain the long cut. Okay, let's take a shortcut. Algebraically, let's see, if I divide everything by n, it'd be 1 over n inside parentheses. top divided by n is 1, bottom divided by n is 1, is 1 over n. So I'm going to raise the top to n to the power, bottom to n to the power. So it's 1 over 1 plus 1 over n to the power. When n goes to infinity, n always goes to infinity. This is the exact definition of E. It's 1 over E. That's the shortcut. And this is less than 1. So we'll say this is going to converge absolutely. So therefore, based on our test, the limit of the ratio is less than 1, so it converges absolutely. Converges absolutely. Now I want to get back to the limit and explain to you the long cut. Okay, so from here, well, I divided, so I realized I would get the E on the bottom when n goes to infinity. But what would you do if you fail to recognize this? Well, you would take the long row, n goes to infinity, you would change the base, so it'd be n log n over n plus 1. Then you apply low beta sort. I mean, you flip, actually. I'm not going to complete. You would flip the n. So you have an indeterminate form here. You apply low beta rule once, you would end up with the same limit here. Alright, so this is how we apply the ratio test to check convergence, absolute convergence of this series. Set up the ratio a sub n plus 1 over a sub n, take the absolute value, simplify, and see the limit. Limit is less than 1, converges absolutely. Now, because in this series there's factorial, so we must use ratio test. Let's see this series. Well, in this series there's no factorial, so we'll probably not use the ratio test. Instead, we see nth power kind of all over the place. That's a good indication that the root test would probably work out the best. There may be other tests we can use. Since we just introduced the root test, might as well just try root test, just because there's an nth power here, nth power here. Okay, so let's set up the limit nth root of absolute value of everything. This is a sub n. Now, under the radical sign, the radical, we take the absolute of everything. That's gone. That's like a positive, negative. Well, just all gone. Become positive for taking absolute value, and the rest of the expression is all positive. So we don't need to have absolute value sign. Then we take nth root. Now you see the advantage of applying the root test. Nth root of 2 to n becomes simply 2. The bottom though is not very obvious. Okay, we're gonna have to take nth root of the n we're going to have to take nth root of 3n plus 1. Now, algebraically, you cannot take nth root of each separately. Okay, there's no such formula. Well, what am I going to do with this? Well, we can estimate. When n goes to infinity, 1 is lower order compared to 3 to the n. That's exponential. So we can drop the 1. Because 1 is lower order. Once we drop the 1, it becomes nth root of 3 to n. That's nicely 3. How about that? Well, we still need to worry about nth root of n. When n goes to infinity, what's this? Let's check on the side. Well, this is basically n to 1 over n power, or we change the base, so 1 over n log n. Now it's clear. This expression will approach e to 0 because log n is lower order compared to n, so it's 1. So basically, nth root of n approaches 1 when n goes to infinity. That's, well, I just proved that. As a matter of fact, we can similarly prove this would approach 1 too for any number a. So nth root of n approaches 1, nth root of any number, in case you want to take nth root, right, of any number, it would approach 1 too. Anyway, so we just showed that this part will approach 1. Therefore, the limit of this expression will be 2 over 3. Less than 1. Coming to our root test. If the limit is less than 1, the original series converges absolutely. After all, we took absolute value of everything to arrive at this conclusion. Converges absolutely. Alright, so these are new tests we learned in this section: ratio test, root test, in addition to the alternating series test for alternating series itself.